Okay, so we're going to move on from the idea of objects hitting each other, at least two moving objects hitting each other, and we're going to look at a simplified case, I suppose, where only one object is moving and the other object is something stationary and effectively immovable, such as a wall. And typically we'll talk about it as being a wall. The title of the chapter is actually direct collision with a smooth plane, but a smooth plane, most intents and purposes, that is a wall, or some plank of wood or something that's fixed and doesn't move. So to start us off with, here's an important question, and one which I'd be quite impressed if you can fully justify. So in the real world, if you throw a ball at a wall, let's say you throw it at the wall at 10 meters per second, it's going to bounce away, and the speed at which it comes back off that wall is obviously going to be less than 10 meters per second. It can't be more, because that would mean that there's been some sort of increase in energy, and it's not going to be exactly the same because some energy will be lost. So energy wise, it makes sense. I throw a ball at a wall, it comes back at a slower speed. But conservation of momentum wise, it doesn't seem to make sense, because as you know, if you take the wall and the ball as two separate objects, then their masses times their velocities, if you add those up, they should stay the same. However, the wall had a zero velocity to start with, and it continues to have zero velocity after you've thrown the ball at it, or at least it seems to. So how do we explain this? It appears to violate the conservation of momentum. What's your explanation? Have a think about it, see if you can correctly justify what's going on. Okay, so hopefully you've paused, you've had a think. In this case, perhaps you're thinking, oh well, maybe the wall does move. Kind of, and I would say yes, it does in some sense technically move, but that's not quite the full story, because even if, say, the wall was 100 times more massive than the ball, right? Say the ball was, a quarter of a kilogram and the wall itself was 25 kilograms, something like this. That still means if you throw a ball at 10 meters per second, you're going to noticeably see the wall move. You might even knock it over. So here, effectively, is the model for what's going on, which makes sense of this. You've got the wall, and you've got the ball going towards it, right? And up until now, we've been thinking, those are supposed to be speed lines there. We've been thinking this is object 1, and this wall is object 2. And we know that the mass of 1 times velocity 1 plus the mass of 2 times the velocity 2 should be constant at all times. So before and after the collision, I should have the same total momentum, right? Momentum is conserved. However, there's a slight correction we need to make to this diagram. This wall, it's not just sitting on the ground. Presumably the wall is connected to something, and that something is connected to something, and so on and so forth. And eventually what you've really got is one very, very massive object, which is an earth attached to a wall. Okay, now that's a bit of a weird looking diagram, partly because it's completely off the scale. But effectively, that's what you've got going on. The wall is fixed to the earth, so really our object 2 is the earth plus wall system, because they're fixed together, and we're assuming for the sake of the model that the fixing together of the wall to the earth is very solid, and the energy is effectively, or the momentum is transferred cleanly, which is a good approximation. So effectively, the mass m2 is the wall mass plus the Earth mass. So what that means is on that scale of Earth to the wall mass system, it's so much bigger, that mass of the wall Earth, that the corresponding velocity when the ball hits the wall is absolutely tiny. Now this itself is a bit of a simplification, it's not quite that simple, but this explains why the wall effectively does not seem to move at all. It technically does, a tiny, tiny, tiny amount, and it's because that momentum is transferred, or that impulse, which is a change of momentum, is transferred to the wall, which itself transfers it, at least to some extent, to the Earth. So when you throw the ball at the wall, to some extent you've ever so slightly modified the momentum of Earth, but to a completely imperceptible degree. So that's the explanation effectively. The wall does technically move, but by a tiny, tiny amount, and it's because it's attached to Earth and transfers that change of momentum to Earth as well. Okay, so we're going to look at the coefficient of restitution again, but this time with this specific case in mind of an object hitting a wall, or if we want to be more technical, a smooth plane. So let's just note down the coefficient of restitution formula again. For two objects, number 1 and number 2, it was final velocity of object 2 minus final of 1 all over initial of 1 minus initial of 2, right? Or remember we had the other version where we just multiply everything by minus 1. So now let's picture the object hitting a wall scenario, and let's say this object, this particle, this ball, this sphere, whatever it is object 1, and let's call the wall object 2, and what we know about object 2 is that before the collision it's that should be u2. Before the collision the initial velocity is 0 and the final velocity is also 0, right? In this model that we're using, where we say effectively that the wall does not move at all, which is a reasonable simplification. Let's then put that into the E coefficient restitution formula, and what do we get? We can put it into either one. Let's put it into this one, and we'll get on the top V1 and on the bottom minus U1. So effectively it's minus V1 over U1. And that's it. So that's our simplified coefficient restitution, which tells us that E just defines the relationship between the initial and final velocity of the one object that's moving, which in this case is the ball or the particle. If you want to put that into words, effectively this is the speed of rebound divided by the speed of approach. Now notice in the wordy way of writing it, we use the word speed, and that's reasonable to do because if you divide a speed by a speed, you're dividing a positive number by a positive number, you get a positive answer. And E is itself always positive, so it makes sense to do that. But how can we have a minus number here? How can we then guarantee that this whole thing is always positive? Well, it's guaranteed because one of these is the velocity before it hits, one of is the velocity after it hits the wall, and it's guaranteed that when an object hits a wall, it's going to change direction. It's not going to go through the wall, not even a little bit. So because the velocity definitely changes direction, one of these, the V1 or U1, is negative and the other one is positive. And therefore when you negate that fraction, you'll always end up with a positive number, right? So this is the total of what's in that circle, or the final result, is definitely positive, right? Because of the fact that an object hitting a wall always rebounds. Okay, so that there is our reduced coefficient of restitution formula. You can just think of it as this: speed of rebound divided by speed of approach. That gives us our E. And remember, it's exactly the same definition. It's still coefficient of restitution. We've just simplified it for a specific case. So let's run through the 3 examples, and then you'll have some time to do some questions. So let's read what it says here. A particle collides normally. Now that word normally, that's a bit of a funny way of phrasing it. By normally, it doesn't mean in the typical way. It means perpendicular to. Okay. Normal and perpendicular are almost synonyms, I suppose. It's just to rule out the possibility that the ball is hitting at an angle, or the particle. So the particle collides perpendicular to a fixed vertical plane. In other words, a ball hits a wall. And the diagram shows the speeds of the particle before and after the collision. Find the value of the coefficient of restitution of E. So pretty simple. 8 is my U1. Minus 2 is my V1, or even we could just say U and V because there's only one object. Minus V1, minus, no, that's correct. Minus V1 over U1 is this, which is a quarter. And that's E, done. Nice and easy. Okay, and here they're just not giving you the diagram and flipping the unknown quantity a little bit. So now we've been given E. If we just read here, the coefficient of restitution between the sphere and the wall is 0.2. So here they've now called it a sphere. So generally this whole chapter, you've got several words that mean the same thing: particle, ball, sphere, and another set of words that also mean the same thing: wall, plane, smooth surface. So this small sphere collides normally with a fixed vertical wall. And again, that fixed, I suppose that's important precisely because it's then telling you the momentum gets transferred to Earth and the wall will not move when you hit it. So before the impact, it's moving with a speed of 4 meters per second on a smooth horizontal floor. In other words, there's no friction, so we don't have to worry about friction in this case. As you could imagine, if friction is involved, it could change the situation a little bit. So with no friction, it's easy, and the coefficient of restitution is 0.2. Find the speed of the sphere after the collision. So U1 is 4, E is 0.2, and we can just plug it straight in to our equation. We get 0.2 equals minus V1 all over 4. V1 equals minus 0.8. So we knew it would be negative because it's gone from moving right to moving left, and the answer is 0.8 meters per second is the speed. Okay, and now in this case, we're not talking about horizontal collisions, we're talking about vertical ones. So when we talk about vertical collisions, we're usually talking about bouncing. And when things are bouncing, we also have to take into account gravity a little bit. So this is the first time we're going to use E, but then also do a little bit of extra work, probably needing some Suvat equations. So a particle falls 22.5 centimeters from rest. That's a bit of a weird way of putting it. Let's call it 0.225 meters onto a smooth horizontal plane. It's from rest, so its initial velocity is 0, and it hits the ground and then rebounds to a height of 10 centimeters. So the path of this ball is to effectively go down and then up and it gets to this point here, which is 0.1 meters. Find the coefficient of restitution between the particle and the plane. Okay, so now we're going to need to use SUVAT and also our E formula. So we want to find the coefficient of restitution, that's E. We know that this is minus V1 over U1. And at this point, because we've done it a few times now, I think we can stop using the 1 subscript and we can just call it V over U, because there's only one object we're interested in. So E equals minus V over U. And this V and U are the same V and U that we use within SUVAT equations. But actually, sorry, not quite. Because here we mean the U is the speed at collision. And this is the speed after collision. So it's not the U, this U is not this 0 here, the initial velocity that it starts at, it's the velocity actually that ends up here. So we've got to be careful to not confuse U's and V's. For now, maybe let's not worry about it too much, and I'm just going to sort of box off these separate bits of work we do, and within here I'm talking about one particular V and U, and within here I'm talking about a different set of V's and U's. So within here we're going to say the distance that it falls is 0.225. So that means I'm implicitly taking down as positive. And you know how to do SUVAT equations. So that's the displacement. The initial velocity is 0. The final velocity, that's the thing we're interested in. That will be the speed at collision. And then acceleration is, well, if down is positive, it's 9.8. We do our SUVAT equation, v squared equals u squared plus 2as. Therefore, v squared equals 19.6 times 0.225. The square root of that will give us v, which in this case is equal to 2.1 on the calculator. So that v is the speed at which the ball is going just before it hits. It's 2.1 meters per second. And then it rebounds, and this E will effectively tell us what the speed that it initially goes up at is. So if it's going at 2.1 going down, so now let's write here, E is equal to that speed at collision is that U on the bottom, so that's 2.1, and then minus, and then that V, that's the speed after collision again, right? So in other words, it's going to be going, on the diagram, it's going to be going up after it bounces at a speed of minus 2.1 E. Okay, and then remember, E is always a positive number, so we seem to be saying it's going up and it's minus 2.1 E, and remember that's because I stated here I'm taking down as positive. To just be consistent throughout, I'm just going to say down is positive in all cases for all values that I'm working with. So that minus 2.1 E makes sense. If down is positive, then a minus number means it's going up. So then we'll set up a new SUVAT equation. In this case, U is minus 2.1 E. That's the initial velocity going up, where E is the number to be found. It reaches a maximum height of 0.1, and at that maximum height we know velocity is 0, because it can be shown that when an object reaches its maximum height, its velocity is at 0. And then the distance travelled is 0.1, but remember, because I'm taking down as positive, we need to put minus 0.1. And acceleration in this case is 9.8. Okay, so then let's do it over here. V squared equals u squared plus 2as. We've got 0 equals u squared is 2.1 e squared. And then we've got 2as, so that's minus 0.2 times 9.8. If we work that out, we get minus 1.96. Okay, so 0 is 2.1 e squared minus 1.96. Actually, it's 2.1 squared e squared. Have to be careful there, almost forgot to square both of them. And that tells me that e squared is equal to 1.96 over 2.1 squared. Square root that, and we should get our e. So in this case, what is that? 1.96 divided by 2.1 squared, and you square root that, and it comes out to a really nice number, which within an exam is a good hint that we're probably going in the right direction. 2/3, that's the value of e. Okay, so then I just want to give you one warning, which is, I suppose, something we've talked about already, but it's this problem with the conservation of momentum and objects hitting walls and the slight inconsistency. Effectively, what I'm trying to warn you about is that when we look at these collisions, when we talked about two objects hitting each other, we would sometimes use Newton's law of restitution and conservation of momentum to find unknown quantities. When we've just got objects hitting walls, don't use conservation of momentum because it's going to fail. And the reason it's going to fail is because of this simplification of the scenario that we've made, which is that we assume the wall doesn't move. So you can use the coefficient of restitution, no problem. We're going to see we can even still use energy considerations. That's fine because it's quite simple to just chalk up any energy differences to it being lost to the environment when the ball hits the wall, but we can't fix the momentum problem. We know that the reality of the situation, it's that the wall and the earth, they have mass and that they move a little bit, but we're never going to be told the mass of the wall, and therefore we're not even going to be attempting to use conservation of momentum. So just a warning, effectively. It's a very useful equation. We can use it for a lot of physics scenarios, but not when we're talking about objects hitting walls. Just ignore it because it's not going to be useful. Okay, so then we've got 3 slides of questions, 1 on the first, 1 on the second, and then 3 on the third. The first 2 slides, very easy. It shouldn't take you long at all. So this slide, you'll be able to knock it out. You can almost do it in your head, these questions, I think. Similar to the second slide, and then on the third slide, you'll have some questions you have to do a bit more calculation, maybe use some Suvat equations, like in the example we just did. So see if you can quickly do this one. Pause the video now. Okay, and then this one as well, you can quickly do it, perhaps even in your head. Can you get the correct U value? Pause the video now. Okay, and then here are the more meatier questions. So you've got a couple there that are exam style questions, and then the last one is a nice challenge question where you're not given any numbers, you're just given an algebraic result to prove, and it's quite a nice, interesting one actually. So see if you can give that a go. Try and do 6/8. See if you've got time for the challenge as well. Pause the video now.